Hello traders, Steve Ganz here, and I want to start a four-part series where I'm going to go back to the basics, if you will, of options trading, and I'm going to take a deeper dive on each of the main Greeks that most of us use in our daily options trading. We're going to take a look in this four-part series. We're going to start here with delta, then we're going to move over to theta, then we're going to look at gamma, and ultimately we're going to look at vega. Those are the four main Greeks that come into play in most of our options trades. Now there are subsequent Greeks beyond that. They call them secondary Greeks in many cases. Not going to really get involved too much in those. But I do want to get through these four and make sure that everybody has a total and complete understanding of them. So with that, I'll get my smiling face off the screen here so that we have the full screen to deal with, and we'll start moving forward. I'm going to go through a series of definitions and some examples, and then we're going to get into some lab time in OptionStrat. So make sure you get all the way through to the end of that, and you can see how you can use OptionStrat yourself for modeling out all of these different variables. Okay, so as we launch into this discussion, it's going to be very important to have a good understanding of these two terms, intrinsic and extrinsic value, as it relates to options. So I'm going to go through and give you some definitions, and then I'll show you some examples and how those play out. So the intrinsic value is the same as the moneyness of an option. Many times you'll hear people refer to an option as in the money, out of the money, at the money. An out of the money option has no intrinsic value at all. Again, we'll look at examples of this in a moment. Extrinsic value is the value of an option beyond its intrinsic value or its moneyness. It's made up mainly of two key components, which we're going to discuss in subsequent videos, and that's going to be the time value or theta decay and volatility. Now, to give you an example, if I own a $100 call on XYZ stock and it's currently trading at $105, the intrinsic value of that call is $5. The extrinsic value is a separate component that's going to vary with time and volatility. Again, to help drive that point home, if we are at expiration and I own a $100 call and it's trading at $105, well, I'm $5 in the money and my option at expiration is going to be worth $5. Now, if there is some time and volatility still in play here, in other words, let's say I am 2 weeks before expiration of this option and I have the same scenario. I've got a $100 call. The underline's trading at 105. I have $5 in extrinsic value in my option, yet that option might be worth $6, $7, $8. That additional above the intrinsic value is the extrinsic value. Again, the extrinsic value is made up of time and volatility, or theta and vega, again, are the two Greeks that represent those two factors of time and volatility. So again, to try to give you a little better understanding of this, out-of-the-money options have a market value less than their premium. This means the option would not be profitable to exercise at that time. For example, if I own a call option that has a strike of $100 and the current stock price is at 90, that option's out of the money and it's not profitable to exercise that option. It wouldn't make sense for me to exercise it, pay $100 a share, and then only sell it for $90. However, an in-the-money option has a market value greater than their premium. This means that the option would be profitable to exercise. For example, if I had a call option with a strike price of 100 and the current stock is trading at 110, that option would be in the money because it would be profitable to exercise that option and then buying the 100 shares of stock and then sell them immediately for 110. And of course, an at-the-money option has no intrinsic value. It will still have some extrinsic value, however, dependent upon how far away expiration is. But at expiration, if you are at the money, there is also no extrinsic value in that stock, and no intrinsic value for that matter. So let's now look at it via a diagram. If XYZ stock is trading at 100 and I own a 110 call, it's out of the money. In other words, there's no value in me exercising a 110 call if the stock is only at 100. Of course, $100, whether I have a put or a call, it is at the money. If I have a $110 put and we're trading at $100, that put is $10 in the money. There is value in that. So hopefully that kind of drives that point home a little bit. Now let's get into delta a little bit, that we understand the intrinsic, extrinsic piece of this pie. So delta essentially equals direction. I think of it that way, that D reminds me, okay, delta is direction or directionality. It's one of the most important Greeks because it measures how much the price of an option is expected to change for every $1 in the price of the underlying asset. Now, I think everyone should know by now that options, any price of an option, that option is per share, but an options contract represents 100 shares. So any numbers I'm going to talk about here essentially need to be times 1 in order to represent the full value of that contract as far as what it would mean to you in dollar terms going forward. So delta is a positive number for call options and a negative number for put options. That's because call options increase in value as the price of the underlying goes up. Put options increase in value as the price of the underlying asset goes down. For example, if a call has a delta of 0.50, that means that the price of the option is expected to change by 50 cents for every $1 change in the price of the underlying asset. And I make this note here, many people will use delta as a rough proxy for a percent chance of the option expiring in the money. And there's nothing wrong with that. It's pretty darn accurate. So if I have something that's a delta of 50-50, not only is that telling me that I'm going to gain 50 cents if my underlying goes up $1, but that also tells me that I'm probably kind of close to center line or about at the money on that option. And there's probably a 50-50 chance that I'm going to be making money on that. As the price goes up, that delta is going to increase. And we're going to see examples of that. And when that delta increases, that gives me a higher percent chance that that option is probably going to expire in the money. Delta is a dynamic measure, meaning that it changes as the price of the underlying asset changes. That's because the value of the option is affected by a lot of different factors, including the price of the underlying asset, or that intrinsic value piece that we talked about, as well as timed expiration and volatility. Delta is a useful tool for options traders because it helps them manage their risk. It helps them understand how the value of their option is going to be impacted as the price of the underlying goes up and down. So it's really important to be able to model that. And again, we're going to do exactly that. We're going to be looking at models of that when we get to the lab section here in OptionStrat in a moment. So to give you an example, again, this is a long call. This happens to be an SPX. And if I have a 4310 long call, we're currently trading at the time I snapped the shot around 4300. This has a delta of a positive 55. Now, at that same rough time in the market that I captured this image, here is if I had a long put. Again, 4310 long put, we're trading at 4308. Well, that's a negative delta. So again, just note the difference here, that we're talking how the delta is measured depending on whether it's calls or puts. So let's go to the lab now. We'll go to OptionStrat and we'll start taking a little bit of a look as to how this models out. Now, the first thing I want to make note of is you can see right down here in the corner, we can model our Greeks in OptionStrat. This is pretty cool that you don't see this in very many places. In fact, this is the only place I think I've ever seen it. So I can come in here, I can model my delta, and I can take a look. This particular trade, for example, now this is as of today on February 8th, 2024. We were trading right about that 5,000 mark in SPX, and I'm using a 49.95 long call, and it happens to be 71 days out. And we can see that right now, that particular delta, if I put my Greeks up here, is right at 60. So again, that means that for every dollar in movement here, this is going to be impacted by 60. Okay, and again, remember everything's times 100. So we can see as I march this forward, or as I move up the scale, as my price gets higher, if I get up here to 5,100, for example, my delta moves up to 75. So again, that is an approximation for how much the price of my option is going to move for each dollar move in the underlying. And of course, that's going to increase. But also, if I'm using that little rough guideline, if you will, I now have a 75% chance that this option is going to expire in the money. And if we not only come up, and if we move forward in time, we're going to see that time also favorably impacts us. That if I come to 5,100, now rather than being 75% chance, I'm an 89% chance that this will expire in the money, because of course there's less time left for this thing to move. And the fact that I'm already up here well above, 100 points above where it was when I entered, my odds of ending there are higher. So we can come in and again model that specifically here until you get all the way down to expiration. And at expiration, you're either in the money or out of the money. There is no in between, which is why it's such a vertical line at expiration. So let me also point out that we can look at this in a table. And we can come into that table and we can see if we're at the money here, which is the 49.98, we can see that delta of 60. And we can see that as time goes on, we get delta reduces a little bit. And then at some point here, it just goes to 100 or 0. Of course, that's at expiration. At expiration, you're either in the money or out of the money. There is no in between. So that's how this progresses. But if we look at a higher number, let's look at 52.50, for example. If I bought this long option and the market jumped up to 52.50 today, that's 250 points above where it is, well, my delta is pretty darn high at that point, which is great. That also means that my likelihood of this thing expiring in the money is now roughly 90%. The closer we get to expiration, the higher that number goes. That's just the way the modeling works. It's going to have a very high percent chance of expiring in the money the closer you get. So we can, again, look at this whole thing in a table format as well. All right, everyone. So thank you so much for taking a deeper dive look into the Greek of delta. The next one we're going to look at is going to be theta. So I'll see you all there.